Good morning students. Today is lecture 28 under module 10. So, in this module we will be discussing basically electrodialysis, pervaporation and we will solve a few problems based on these two topics. So, in today's class is exclusively dedicated to ion exchange membranes and electrodialysis. So, let us begin. So, we have discussed in our earlier class what is ion exchange membrane, right. So, we have learned what are the different types of ion exchange membrane. So, we will just quickly go through this so that you can revise what we have been discussed earlier also. So, an ion exchange membrane is a semi permeable membrane that allows the passage of certain dissolved ions while retaining other ions. So, selectively it will pass certain ions, dissolved ions, whereas retaining the other ions. So, the basic desirable characteristics of ion exchange membrane are as follows: high permeability of oppositely charged ions. So, oppositely charged ions, all of them must pass through the membrane, which is actually eventually not happened in a real life system. Then high ion permeability, that is low electrical resistance, that means conductivity to counter ions and does not unduly restrict their passage. High form of stability or low degree of swelling, mechanically strong and robust and must not wrinkle or deform under thermal stress. So, these are some of the features of the ion exchange membranes. Now, the membranes used in electrodialysis process are essentially consisted of sheets of ion exchange polymeric resins. So, they may also contain other polymers to improve mechanical strength and flexibility. So, it may happen many times. So, they are stacked. It may be a membrane having a particular ions imparted into that. If it is cation exchange, or it can may be anion exchange, it may be bipolar also. We will discuss this later. Okay. So, in between also there may be other layers of polymers fused in between to improve the mechanical strength and flexibility. So, in the interstices of the polymer are mobile counter ions. So, the counter ions are in a mobile phase are placed in between the interstices of these polymers, layers of polymers basically. The resin components of a cation exchange membrane would have negatively charged groups. Okay. So, that is anions. So, cation exchange means it is exchanging cations, so it has fixed anions groups. Anion exchange means it is exchanging anions, so it should have fixed cationic groups. So, these groups, either positive groups, cations or anions, are fused together or attached together to the polymer resins. By that there are different methods actually to do that. That also we will discuss later. Okay. So, ions with a charge opposite to the fixed charge are freely exchanged at these sites. So, let us see, this is the schematic representation of an anion exchange membrane and a cation exchange membrane. As you can see this is the first one is the anion exchange membrane. Okay, here you can see this fixed cationic groups are present. So, it is exchanging anions, that means anions are getting transported, whereas the cations are fixed inside the polymeric resins. So, inside the polymeric resins, the interstices of the polymeric layers. So, these cationic groups are present in a mobile phase. The case is same for the cation exchange membrane. So, here the anions are fixed, right, and the cation is getting transported. So, this is how actually a cation exchange membrane or a anion exchange membrane works, right. So, this is an example of a cation exchange and anion exchange membrane in a direct borohydride and peroxide fuel cell, right. So, you can see this, the membranes, how do these membranes operate? So, they operate by this Donan exclusion principle. So, membrane operate according to the principle of this Donan exclusion. That means, what is the meaning of that? So, that means only transfer of oppositely charged ions is allowed. Okay. So, you can see this in the first figure, the solid lines, right. The solid lines represent the oppositely charged migration of the ions through the membrane, while the transfer of the ions of the same charge as immobilized membrane group is mostly blocked. So, this sodium, you can see here potassium. Okay. So, mostly they are blocked because they are oppositely charged. Okay. Since the concentration of the counter ion is relatively high, they carry most of the electric current through the membrane. So, the fixed charges attached to the polymer chains repel ions of the charge, that is coions, in this case anions. Okay. Anions carry only a small fraction of the electric current through a cation permeable membrane, as their concentration in membrane is relatively low. Now, again one more important thing that has to be remembered is this: whenever we are talking about ion exchange membranes, as we discussed that either cations or anions are present in the mobile phase inside the membrane matrix. So, how much amount of these cations or anions are present, that also plays a big role in deciding the permeability or the transfer of the oppositely charged ions. So, this also plays a very big role, the concentration of the ions. So, attached to the fixed charge, that is R equals to CH3 group actually, to the polymer chains form anion permeable membrane which are selective to transport of negative ions, because the fixed ammonia group repel positive ions. The meaning of Donald exclusion is actually allowing the passage of opposite charged ions. So, the bulk solution contains a large excess of available sodium plus ions with an effectively constant concentration. Okay, you can see this sodium ion is not getting properly transport through the membrane, okay, through the anion exchange membrane. So, a static layer of the solution known as the Nernst film surrounds the beads. Ion transport takes place by diffusion only. Strong convention, that is high flow rate, decreases film thickness. This is true for other membrane separation process also. The ion concentration gradients occurs within it. Diffusion through the film and in the solid phase occurs at different rate. Two steps may be rate determining in ion exchange membranes. So, the first is diffusion through ions within the resin. So, this is called particle diffusion, and the second is diffusion in the Nernst film, that is called film diffusion. Now, ion exchange polymers such as polystyrene sulfonic acid are water soluble and are cross linking, and so cross linking is required to prevent dissolution of ion permeable membranes. Why we are talking about cross linking? Because if you do the cross linking, then these charged groups will be almost permanently attached to the surface of the membrane, okay, right, or the polymers. So, if it is not cross linked properly, then groups like sulfonic, this polystyrene sulfonic acid, they are water soluble. So, when you are using it for the desalination purposes, most of these groups will come to the water side or to the aqueous medium. So, your ion exchange will initially, though it will start, then slowly it will decrease. Divinyl benzene is used to cross link polystyrene chains. Higher cross linking improves the selectivity and membrane stability by reducing membrane swelling, but at the same time it reduces electrical resistance also. High charge density reduces resistance and increases the selectivity, but it promotes swelling and thus necessitates higher cross linking. So, higher cross linking and higher charge density, so you need to optimize it. So, some sort of optimization is required, so that cross linking is also good and charge density is also good. A compromise between selectivity, electrical resistance and dimensional stability is achieved by proper adjustment of cross linking and fixed charge density. This is what I was just telling, that some sort of optimization is required to have a proper or good cross linking as well as have fixed charge densities. A typical electrodialysis membrane has a pore size of 10 to 20 angstrom with a capacity of 2 to 3 milliequivalent per gram DW resin. So, membrane thickness is of the order of 0.1 to 0.6 millimeter and the electrical resistance is approximately 3 to 30 ohm per centimeter square. So, based on the distribution of fixed charges over the polymeric matrix, ion exchange membranes can be further classified into homogeneous membranes and heterogeneous membranes. So, in homogeneous membrane, the fixed charges are distributed homogeneously, right. They can be prepared by the following methods. So, graft polymerization of anionic or cationic moieties onto the molecular chains of the film or polymerization of mixture of reactants. So, in the first one, directly the moieties, that means the cationic and anionic groups, the ions itself are being grafted on the surface of the polymer. So, in the second case, it is a polymerization reaction. Okay. So, here mixture of reactants like let for example, phenol, phenyl sulfonic acid, formaldehyde, okay. These are reacted and they form these cationic anionic groups. So, because they undergo the condensation polymerization reaction. Then another one is introduction of anionic or cationic moieties into the polymer chain such as polysulfone, followed by the dissolution of the polymer and casting into the films. So, these are the way on how you can prepare homogeneous membranes. The heterogeneous membranes can be prepared by incorporating ion exchange particles into film forming resins by the following methods. So, either you can have dispersion of the ion exchange materials in a solution of the film forming polymer followed by film casting and solvent evaporation. So, how do you actually prepare the polymer solution, how do you cast it, then solvent evaporation, all these things we have discussed during our membrane preparation techniques. I am not repeating it. So, then dry molding of mixtures of the ion exchange and film forming materials. Homogeneous ion exchange membranes have relatively low electrical resistance and high mechanical strength, rendering them as better candidates for electrodialysis as compared to their heterogeneous counterparts. So, the next is bipolar membranes. So, they are very interesting actually. So, bipolar membrane consists of an anion permeable membrane and a cation permeable membrane joined together. So, there is a cation exchange membrane and the anion exchange membrane, they are joined together. Just see how it is being joined here, okay, right. So, this is your anion exchange resin and this is your cation exchange resin or layer or membrane you can call them. So, when this composite structure is oriented in such a way that the cation exchange layer faces the anode, okay. So, if you are fusing them, then the cation exchange layer is facing the anode, it is possible by imposing a potential field across the membrane to split water into proton and hydroxyl version. This is a classical example of water splitting reactions. You can see water is getting split to protons and hydroxyl ions. Okay. So, this result in the production of acidic and basic solutions at the surface of this bipolar membrane. Now, compared to the conventional electrolytic cells, the bipolar membranes are inexpensive. Okay. So, that is why they are gaining a lot of attraction nowadays. The bipolar membrane offers the prospect of low cost, okay, as well as minimum unwanted byproducts. So, here the byproduct formation is very less, right, and the cost is also low. So, they are gaining more acceptance in industries. The resistance of ion exchange membrane is in the range of 2 to 10 ohm per centimeter square and fixed charge density is about 1 to 2 milli equivalent per gram. Now, let us discuss electrodialysis, what is its concept. So, you can see closely look at this particular figure. So, electrodialysis actually began in the early 19th century as a modification to the dialysis by addition of electrodes. We have discussed what is dialysis. Now, just imagine that dialysis is happening under the presence of an electrical gradient and there are two electrodes present, one cathode and one anode. Why do we do that? To increase the rate of dialysis in for a electrolyte solution. Now, electrodialysis refers to an electrolytic process for separating an aqueous electrolyte feed solution into a concentrate or brine and a dilute or desalted water by means of an electric field or ion selective membrane. So, you can see here this is a simple electrodialytic cell, dialysis cell. So, here there is a cathode, there is a anode and there are two membranes. Okay, one is cation transfer membrane or cation exchange membrane, another is anion transfer or anion exchange membranes. Okay. So, you can see that feed is coming from here, okay, the seawater basically. So, you can see that sodiums are getting transferred here in this chamber. So, it is getting concentrated here, whereas chlorines are getting concentrated in this chamber particularly, and whatever water you are getting here. So, that is pure water because it is devoid of sodium chloride now. So, this is a classical example of the schematic diagram of the electrodialysis process. So, here there is a cathode, there is a anode and I have shown here 4 stacks of 4 membranes, 4 different types of membranes. So, you can see the C stands for the cation exchange membrane, A stands for the anion exchange membrane, okay. Again a cation exchange membrane. So, there are 2 stacks basically. So, in ED process a stack means one cation exchange membrane, one anion exchange membrane and then maybe a cathode and anode. Now, the cathode and anode may be same. So, in between we can have many cation exchange membranes and anion exchange membrane. Here I have shown you 4. Okay. So, we have 2 cation exchange membranes and 2 anion exchange membranes, okay, arranged in series something like this, right. Then your feed solution actually being circulated here. So, this is feed, it is entering here, okay, and this is compartment 1, this is compartment 2, this is compartment 3, this is compartment 4, this is compartment 5th. Okay. So, the concentrated solution we are getting in compartment 1, compartment 2 and compartment 4, whereas the dilute solution is dilute that is devoid of your ions, basically we are getting from compartment number 3. Okay. So, let us see the discussion. So, this figure demonstrates a typical electrodialysis process where 4 ion selective membranes shown are of 2 types arranged in alternating series pattern. So, the cation selective membrane carry a negative charge and thus attracts and pass positively charged ions, whereas regarding the negative ions. So, here cation selective membrane C, this C, okay. So, it carries, okay. So, C is carrying a negative charge, right. So, it is passing cations, that means it has negative charges, okay. So, these are negative charges, okay. So, it is passing cations, that is why, right. Similarly, a anion exchange membrane it carries positive charge, right. So, what it is doing? It is passing here anions, right. So, you can see the anions are passing right here, here the cations are passing. Okay. So, cation exchange membrane is exchanging or passing the cations, anion exchange membrane is passing the anions. So, both cations and anions in a stack of two membranes, okay, all the ions are getting concentrated here. So, you get concentrated solution here. Similarly, we get concentrated solution here. Okay. Right, all the concentrates are here, then coming and getting collected here. Okay. And in this particular this one stack or space, the chamber 3, you can see hardly any ions are there, because whatever the ions are coming here, the feed sodium chloride. Okay. The cations are passing through this cation exchange membrane, here the anions are passing through this membrane. So, here there is a anode and there is a cathode, and the electrical potential is applied. So, both types of membranes are impervious to water. So, this is important. Okay. So, the net result is that both anions and cations are concentrated in compartment 2 and 4, from which the concentrate is withdrawn, and the ions are depleted in compartment 3, from which the dilute is withdrawn. The compartment pressures are essentially equal. Compartment 1 and 5 are bounded on the 4 sides by anode and cathode respectively. So, a direct current voltage is applied across the anode and cathode, causing current to flow by metallic conduction of electrons through the cell by ionic conduction from cathode back to the anode. Both electrodes are chemically neutral metals, okay, with the anode being typically stainless steel and the cathode is typically platinum coated tantalum, niobium or titanium. Thus, the electrodes are neither oxidized or reduced. Typically, the most easily oxidized species is oxidized at the anode and the most easily reduced species is reduced as the cathode. At the cathode is the reduction of water by half reaction. Okay. So, you can see this reaction 2 water plus 2 electrons giving 2 hydroxyl ions plus hydrogen in the form of gas. The oxidation half reaction at the anode is water giving 2 electrons plus half oxygen in the form of gas plus 2 protons. So, if chloride ions are present. So, this is important, again most of the times chloride ions are present. Okay. So, 2 chlorine giving 2 electron plus chlorine in the form of gas, where the electrode potentials are standard values at 25 degree centigrade for 1 molar solution of ions and partial pressures of 1 atmosphere for the gaseous product. So, value of E can be corrected for non-standard conditions by the Nernst equation. Okay. The corresponding overall equation can be written as 3 waters giving hydrogen in the form of gas plus half oxygen in the form of gas plus 2 protons plus 2 hydroxyl ions, or 2 water plus 2 chlorine if chlorine is present gives 2 hydroxyl ions plus hydrogen in the form of gas plus chlorine in the form of gas. The net reaction for the first case is water, okay, is splitting into hydrogen in the form of gas plus half oxygen in the form of gas. So, the electrode ring solution that circulates through compartment 1 and 5. Okay. So, just trying to show you again, there is something called the electrode ring solution dotted by this red line, you can see this. Okay. So, this electrode ring solution is actually circulated through compartment 1 and 5 is typically acidic. Okay. What is its job? So, it has to neutralize the OH minus ions, okay, formed in the compartment 1 and prevent precipitation of compounds such as calcium carbonate and magnesium hydroxide. Okay. So, as you know that we have different types of membranes. So, we can have cation exchange membranes which is having negatively charged fixed groups, and anion exchange membranes which is having positively charged fixed groups for the electrodialysis membrane purposes. A typical cation selective membrane is made up of polystyrene cross-linked with divinyl benzene and sulfonated to produce fixed sulfonate groups, SO3 anion groups. An anion selective membrane of the same polymer contains quaternary ammonium groups such as NH3 plus. Membrane are 0.2 to 0.5 mm thickness and reinforced with a screen to provide mechanical stability. Mechanical stability is very important because when you are going for a continuous operation, so the stability of the membrane also has to be taken care of, because there is some pressure is always that is getting developed inside the electrodialysis cell, though we are not pressure driving the system. However, to withstand the thermal, mechanical, all these types of pressure, so the stability of the membrane is very important. So, the membranes which are made in flat sheets contain 30 to 50% of the water and have a network of pores too small to permit water transport. A cell pair or a unit cell consists of one cation selective membrane and one anion selective membrane. So, one cation selective, one anion selective and one cathode. So, basically one cation selective, one anion selective then one cathode, okay, and one anode. So, this is what is called a pair or unit cell of a single electrodialysis system basically. So, a commercial electrodialysis system is a large stack of membranes patterned after a plate and frame configuration. So, for a commercial systems we have CA, 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 CA like this, okay, alternatively in series, right. Then we have here anode, we will have here cathode, right. Okay. So, you applied electric potential and then do the separation. Now, please remember that we cannot increase the number of the cation exchange membrane and anion exchange membrane just infinitely, okay, with a single cathode and single anode, that is not possible. Okay. So, there is always a optimization that you need to do it. Okay. With a single anode and a single cathode, maximum number of cell pairs you can have. For a targeted separation. So, in a stack, membranes of form 0.4 to 1.5 meter square surface area, each are separated from 0.2 to 2 mm with special gaskets. The total voltage or electrical potential applied across the cell includes the electrode potentials that we have discussed earlier, over voltage due to gas formation at the electrode, the voltage required to overcome ohmic resistance of the electrolyte in each compartment, the voltage required to overcome resistance in each membrane, the voltage required to overcome concentration polarization effect caused by mass transfer resistance in electrolyte solution adjacent to membrane surface. And for large stacks, the latter 3 voltage increments predominates and depend upon the current density, that is the amps flowing through the stack per unit surface area of the membranes. A typical voltage drop across a cell pair is about 0.5 to 1.5 volt. Current densities are in the range of 5 to 50 milliampere per centimeter square, thus a stack of 400 membranes. So, basically 200 unit cells of 1 meter square surface area each might require 200 volt at 100 amperes. So, typically 50 to 90% of brackish water is converted to potable water depending on concentrate recycle. As the current density is increased for a given membrane surface area, okay, the concentration polarization effect increases. So, concentration polarization effect for a cation exchange membrane is being shown here. Okay. So, here Cm refers to the cation concentration in the membrane, Cb refers to the bulk electrolyte cation concentration, the D and C refers to the dilute and concentrated site respectively. The maximum or limiting current density is reached when the Cm in dilute site reaches 0. Typically, an electrodialysis cell is operated at 80% of the limiting current density, which is usually determined by experiment. The corresponding cell voltage or resistance is also determined experimentally. The amount of gases formed at the electrodes at the two ends of stacks are governed by the Faraday's laws of electrolysis. So, during electrolysis, 1 Faraday, that is exactly equal to the 96,520 coulombs of electricity reduces at cathode and oxidizes at anode, an equivalent of oxidizing and reducing agent corresponding to transfer of 6.023 into 10 to the power of 23, that is the Avogadro's number of electrons through wearing from anode to cathode. So, this is the amount of electricity that is getting passed. In the design and operation of electrodialysis membrane process, the membrane area and electrical energy requirement are important. The membrane area is estimated from the current density by applying Faraday's law. So, this is the equation. So, AM equals to F Q delta C by I zeta, where AM is the total area of all cell pairs in meter square, F is Faraday's constant, Q is volumetric flow rate of the dilute, so which is actually the potable water in meter cube per second. Delta C is the concentration difference between the feed dilute ion concentration in equivalents per meter cube. I is current density in amperes per meter square of the cell pair, and zeta is the current efficiency, which is usually less than 1. So, the last variable accounts for the fact that not all of the current is effective in transporting the selected ions to the membrane. Now, inefficiencies are caused by this Donan exclusion of less than 100%, some transfer of water through the membranes and current leakage to the manifolds. So, you devise any sorts of membrane basically, as we have discussed that most these membranes are impermeable to water, but in actual practice when there is some pressure getting developed inside the membrane, so some inside the system, so some water passes through. That is against the principle of 100% Donald exclusion. Okay. and there are leakages and other things also. So, power consumption can be calculated by P equals to I into E. So, P is the power in watts, I is electric current flowing through the stacks in amperes, E is the voltage across the stack in volt. The electrical flow is given by I equals to F Q delta C by N zeta. So, the main application of the electrodialysis is to desalinate brackish water in the salt concentration of usually 500 to 5000 ppm. Now, below this range, so that means below 500 ppm ion exchange is more economical, okay, and above 50,000 reverse osmosis is better. Okay. This we have discussed in reverse osmosis also. However, electrodialysis cannot produce water with a low dissolved solid content because of the high electrical resistance of the dilute solutions. So, apart from desalination of brackish water, there are other applications also. So, recovery of nickel and copper from electroplating rinse water, deionization of cheese, whey, fruit juices, wine, milk and sugar molasses, separation of salt, acids and bases from organic compounds and recovery of organic compounds from their salts. Bipolar membranes prepared by laminating a cation selective and anion selective membrane can be used to produce sulfuric acid and sodium hydroxide from a sodium sulphate solution. Now, let us understand the energy requirement, current utilization and efficiency. The energy required for the removal of salts from a feed solution is directly proportional to the total current flow flowing through the stack and the voltage drop between the two electrodes in a stack. So, according to the basic equation of the ohm, V equals to IR. So, V is voltage in volts, I is current in ampere, R is resistance in ohm. So, again I is nothing but Q by T. So, Q is the charge in coulombs and T is time and E equals to V I T. So, E is energy consumption, I is your current and T is your time. So, if you combine these three equations for n number of unit cells, so we can write E equals to I square n R T. Since resistance in the dilute and concentrated parts of the cell differs from each other, the resistance per unit cell R can be taken as an average cell resistance, right. So, therefore, E equals to I square n T. So, R concentrated plus R dilute divided by 2. So, each chamber is completely mixed. So, in general resistance is approximately inversely proportional to the concentration, R equals to B by C, where B is a constant, okay, and C is your concentration. So, after some algebraic manipulation we will get in this equation E equals to I square n T R C F divided by C F minus C dilute by C F whole square, where R C F is the resistance per cell determined at the feed concentration. Further, electric current needed to desalt a solution is directly proportional to the number of ions transported through the membrane. It can be expressed as I equals to Z F Q C F minus C dil by zeta, where F is Faraday's constant, Z is electrical valence, Q is volumetric flow rate, Cf minus C dilution is concentration difference between the feed solution and the dilute, and zeta is the electrical utilization. So, the current utilization is the most important term in this equation. It is directly related to the number of cells n in a stack and the efficiency of utilization of the current. So, if you combine the equation 5 and 8, so you get equation something like this, where R average equals to R concentrated plus R diluted divided by 2. Now, this equation indicates that electrical energy required in electrodialysis is directly proportional to the amount of salt that has to be removed from each feed solution to achieve the desired product concentration. So, energy consumption is also a function of the number of cells in a stack and the electrical resistance in a cell. Electrical resistance again is a function of individual resistances of the membrane and of the solution in the cell. Now, the current utilization is directly related to the number of cells by this equation. So, you can write zeta equals to n eta s, eta w, eta m. So, where n is the number of unit cells, eta s is the efficiency due to the semi permeable of the membrane, that is there is a membrane constant basically, eta w is the efficiency related to water transfer through the membrane, and eta m is the efficiency since some of the current invariably leaks through the manifold holding the membrane. So, eta s is the semi permeability membrane thing, eta w is the water transfer capability, and this is about the current. So, all the efficiencies are less than unity and the overall electrical efficiency is about 0.9, but n varies from 100 to 600, depends upon what type of commercial establishment it is. So, the zeta is usually higher than unity. The membrane area for cation and anion exchange membrane can be estimated from this equation: A equals to F Q N Cf minus CD divided by I zeta, where I is the current density and the membrane area A is related to the area of each individual membrane given by A equals to N AM. Okay, where AM is set by the dimensions of the plate and frame module, which are standardized by the manufacturers. So, substituting we get this is the final equation. Okay, N equals to F Q Cf minus C dilute divided by eta I, eta S, eta M and eta W. So, we can have our electrodialysis process operating in two modes. Either you can have a batch mode or you can have a continuous mode. Now, batch mode are easy to operate, that is true, but the problem is that the pressure this one, the power consumption will rise. Okay, now let us see how we can have a batch mode operation. So, you can have a, so let us say this is our electrodialysis membrane setup. So, then you will have a cathode here, we will have a anode here. Okay. Right. So, of course, cathode and anode are connected to a DC source, right. So, then what will happen basically? So, you will be passing or pumping, there is a feed tank here, okay, from which the feed is getting pumped and it is getting inside the membrane, okay, right. And there is another tank, okay, which is concentrate. You need another pump here, okay, to pump the concentrate here. Okay. So, what you will get from here is dilute, okay, and whatever you will get here is your concentrate, right. So, what is happening in this batch mode of system is actually the power consumption rises with the process because of the voltage drop over the cell increases. Okay. Now, it is also possible to run an ED process in a continuous mode also. To decide whether we will have a batch mode or a continuous mode, the stack design has to be taken into account. Now, you can have this process in a continuous system also, just trying to draw a continuous system. Okay. So, again a cathode here, again a anode here. Okay. So, this is anode, this is cathode, they are connected to a DC source, okay, right. So, and then we will have a pump, we will have two pumps basically. So, this pump is pumping your, this is your concentrate, this is its dilute. Okay. So, you will get a dilute out here and here concentrate out, and this is in and this is in. Okay. So, this is the continuous mode of operation, it is easy to do that. Okay. Now, your stack design and there are other operating parameters which will eventually decide whether you will go for a batch system or a continuous system. Now, if you want to run the module electrodialysis module in a continuous mode, the module has to treat the solution in one go. Okay. Why the batch? In the batch process what is happening, if you go back in the batch process what is happening. So, when you are passing the dilute and concentrate in a single stage, okay, what is happening that you are not at all getting your targeted separation, okay, or a targeted purity, whatever you can call it. So, you have to pass the same solution, the concentrate and dilute many times to achieve your target, okay, in the same membranes. So, it is going on in a batch process, but many times, right. So, eventually what is happening, by doing so the power consumption rises, okay, because there is a voltage drop over the cell increases. So, here in case of continuous system, so this is not happening. and it is necessary to assign a certain time and certain velocity of this solution, okay, both dilute as well as concentrate. Okay. And it is also important that the residence time in between inside the electrodialysis cell is enough, so that a proper separation is happening. So, this is how ED can be operated in batch and continuous mode. Now, let us understand the applications. There are many applications. The most important application is of course the desalination and conservation of sea, brackish and industrial waters. So, electrodialysis is widely used in desalination of brackish water, where the concentration of the salt is usually 500 to 5000 ppm. So, in this process the salts are concentrated to comparatively high values. The process is unique in Japan, whereby law it is used to produce essentially in all of its domestic table salts by the means of electrodialysis. Then we can have separation of inorganic and organic solutions, purification of organic substances such as amino acids, then wastewater treatment and recycling of chemical substances. So, in electrodialysis it is an alternative process for treatment of wastewater, since it allows the reuse of the process water, and this is the most important thing, allows the reuse of process water and the recovery of metal ions, minimizing or even avoiding the production of galvanic sludge. So, this is a very important thing. So, then in galvanic industries, so in galvanic industry ED can be used for regenerating the metal finishing baths and wastewater treatment. So, apart from that, in food industry the application is demineralization of cheese whey and wine stabilization. So, whey provides an excellent source of protein, lactose, vitamins and minerals, however it has high salt content. So, with ionized salt substantially removed, whey approaches the composition of human milk and provides an excellent source for the baby food. So, wine stabilization is another application of electrodialysis process in your food industries. So, it involves the removal of tartaric acid from wine. So, tartaric acid has to be removed from the wine. Okay. In the production of the bottled champagne, essentially it is necessary to avoid the formation of crystalline tartar in the wine, and tartaric acid must be reduced to a level that does not exceed the solubility limit. Okay, otherwise it will form crystals, and you can clearly see that there are some crystals getting deposited on the bottom of the wine bottle or champagne bottle. So, next in the food industries is the production of artificial mother's milk. Now, when comparing mother's milk with cow's milk, the ash content is 3 times higher and the protein content is 6 times higher in cow's milk. So, therefore, when cheese whey, the leftover after the cheese protein is removed from cow's milk, the fresh cow's milk are combined. The protein content become almost equal to the mother's milk. Then we have application in desalination of fruit juices also and desalting of dextran solution also. In the pharmaceutical industries also, we have application in purification of fermented solutions, serum and vaccines. There are other uses like regeneration and recycling of galvanic baths. In the production of printed circuits, a chemical process is often used for copper plating. The component to be placed are immersed in a bath containing copper salt solution, formaldehyde and EDTA. Now, during this process, formaldehyde is oxidized to formate. After prolonged use, the bath becomes enriched with sodium sulphate. Formate loses useful properties. So, by applying electrodialysis in a continuous mode, the sodium sulphate and formate can be selectively removed, okay, from the solution without affecting the concentration of formaldehyde and EDTA complex. Then purification of salty mine water. So, there is a current need to evaluate the use of electrodialysis on the treatment of wastewater with the aim of scaling it up to industrial operation. However, it is important to understand the behavior of such a system either in laboratory or pilot plant condition. Recovery of valuable electrolytes is another application. So, electrodialysis can be successfully used in the recovery of various electrolytes. So, it can recover pure sodium chloride from seawater, then silver salts from photographic waste, then nickel from electroplating rinse waters, zinc from galvanizing rinse water, salts of organic acids from fermentation broth, amino acids from protein hydrolysates, acids from metal pickling baths and rinse hydrochloric acid from cellulose hydrolysate. So, you can see that there are so many applications of electrodialysis. Some important applications further includes that rinse water treatment from plating industry of metals like chromium, cadmium, nickel, recovery and concentration of ions, okay, from wastewater and supply the global demand of macronutrients. This technique not only concentrates metals from rinse water, but it also maintains the quality of a plating bath. That is also very important to concentrate the nutrients from waste stream. So, students, this is taken from this one of the journal publications. So, just to show you and understand that the timeline of the most critical development of the electrodialysis process and related processes. So, it started with 1890, long back. You can see that the first ED concept by Maigrot and Sabates. So, these are the two scientists who has conceptualized the electrodialysis process. Then in 1900, okay, the word electrodialysis appears for the first time. In 1911, Donan exclusion theory was proposed. In then after a huge gap of almost 40 years, multi-component electrodialysis concept and the first synthetic ion exchange membranes were fabricated. Then in 1954, first ED plant by Ionics was established. Then in 1974, after a gap of almost 20 years, EDR development by Ionics. Okay. Ionics is the company which is manufacturing the ED plants. Then 1987, first commercial use of BPM at Washington Steel in Pennsylvania was reported. Then first CED production by Millipore also reported in 1987. Then slowly electrodialysis proposed for zero liquid discharge, the first lab scale RED unit with captive electrodes, shock ED proof of concept, and all these things has come into picture. Okay. And in 2015, recently coupling electrodialysis with wind, photovoltaic and reverse electrodialysis system has been proposed. Now, students, let us understand what is reverse electrodialysis. So, we have discussed ED, what is RED or reverse electrodialysis. So, it is a technology to generate electricity, it is very important. Okay. In the ED, we are not generating electricity, but here the concept is same, but we can generate electricity from the salinity difference between the two solutions, that is sea water and river water. Now, what is being done is that you can see this particular, there is a cathode, there is a anode. Okay. Then you are feeding your sea water here in this chamber 1. Okay. And chamber 2, and you are feeding fresh water, that is river water. Okay. If you take this is chamber 1, chamber 2, chamber 3, chamber 4. Okay. So, in chamber 1 and 3 you are feeding your salt water. Okay. That means the feed is being feeded or being transferred to the stacks. Okay, in such a way that it goes between one cation exchange membrane and one anion exchange membrane, and on the interspaces between two stacks. So, this is one stack, this is another stack. Similarly, this again another stack will go on. Okay. So, in the interspaces between these two electrodialysis stacks, so we will be feeding fresh water. Okay. So, this is fresh water, right, or river water. So, what is happening is that, so this system is composed of an ion exchange membranes and compartments for sea and river water in alternating order. The ion exchange membranes are selective for either cations or anions. The salinity difference between sea water on one side and river water on the other side of the membrane creates a potential difference. So, basically the potential difference is aroused because of the concentration of the ions in the sea water as well as river water, or the salinity difference in the crude way you can tell that. Multiple cells each comprising a cation exchange membrane, a sea water compartment, an anion exchange membrane and a river water compartment can be piled up to increase the voltage. So, electrodes at both ends of the pile facilitates a redox reaction which generates an electrical current to power an external device. So, RED is an electrochemical separation process that allows selective passage of ions or charged species in solutions. Only anions or negatively charged ions can pass through anion exchange membrane, while cation exchange membrane transport positively charged ions. So, this is same, this we have discussed in the earlier also. So, ions are transported through the ion exchange membrane by means of direct current voltage and are removed from feed water as the current drives the ion through the membrane to desalinate the process stream. And the RED or the reverse electrodialysis system reduces the fouling tendencies of the water by reversing the polarity of the electrons in every 15 to 20 minutes. So, this is an greatest advantage of the electrodialysis, reverse electrodialysis system. The change in polarity causes the scale to dissociate from the membrane. So, there is no scale formation that is going to happen on the surface of the membranes. So, the RED process can successfully remove arsenic, radium, perchlorate as well as desalination of well and surface water. The application of RED includes municipal drinking water, industrial process water and wastewater reuse projects. For wastewater reuse projects, the reverse electrodialysis process is ideal because of the rugged membrane and high chlorine tolerance. Okay, so, this is another historical development of the RED technology. You can see that it started from 1954. Okay. just after the first electrode ion exchange membrane was fabricated. Okay. Then in 1976, the first theoretical model of RED in ion exchange membrane was established. The concept of harvesting SGP and RED was first described by Patel. Okay. So, then in 1986, a hybrid RED desalination facility, solar power was proposed. Okay. Then you can see there are, you can just go through it later on. So, then microbial RED cell was reported in 2011. Okay. The first tailor made anion exchange membrane were tested in RED. Okay, that is in 2012, and the latest development is coupling RED in electrodialysis in a single stack was explored for energy self sufficient desalination. That means, you know, the RED, the ED is doing desalination, the RED is producing energy. For desalination we need some energy, that energy will be replenished or will be supplied by the RED. So, that means one ED system and one RED system is being coupled together, so that the RED will provide the energy that is required for the ED, so that it becomes the self sufficient desalination plant. And very recently, okay, we can see that the RED plant was established for using saline concentrated brine. This is already this one. So, closed loop RED for waste fat recovery is also being proposed. Then profiled ion exchange membranes with ridges structure were applied in RED, ridges or something like that. Okay. So, anyway, we are not going into detail about this, just the idea is to make you understand that how RED and how ED has developed gradually and successively. So, with this I wind up. Most of the things are taken from different books like Kanath, and there are other books also. Okay. So, please go through the lecture, and if you have any doubt, please feel free to write to me at kmohanty@itg.ac.in. So, in the next class we will be discussing one of the classic membrane separation process, which is called pervaporation. So, its basic principle, advantages, membranes and modules, how mass transfer is happening in pervaporation, different pervaporation applications, then hybrid distillation and pervaporation. So, thank you very much.